Hello everyone. Let's continue our discussion on threshold voltage. Let us take a moment out to revise what we did in the last couple of lectures. So what we did was we introduced you to an NMOS structure. It had got heavily doped N plus source, heavily doped N plus drain, and it had got 4 terminals: source, drain, gate, and the body terminal, and it was built on a P-type substrate. Also, we had got some isolation region just to isolate this particular MOSFET from its adjacent MOSFET. And the gate was referred to as polysilicon or metal gate, and this was the gate oxide. This led to a formation of a parallel plate capacitor. Next, what we did was we were trying to learn the threshold voltage, and we said that threshold voltage is nothing but the voltage at which your device turns on. Let's try to prove that in this video. And initially what we did, we tied the source, drain, and the body terminal to ground and applied a positive potential to the gate terminal to see what happens. And what happened was, in this particular plate of the capacitor turns positively charged, and it tends to behave like a magnet. It tries to repel all the holes from the p-type substrate, which is its majority carriers. And when you see its majority, when you see the p-type substrate, when you see this area getting depleted of its majority carriers, this particular junction behaves like a classic PN junction diode. So we saw all this in the last videos. So we'll start continuing from that particular point where we have applied a positive gate voltage over here and see what happens. So in this one, what we'll be doing is we'll be increasing the positive gate voltage. We'll be increasing the gate voltage over here. So this is what we call it as a depletion region, which is behaving very similar to a PN junction diode. So PN junction diode also, when you keep it at reverse bias, you see the p-type area gets depleted of its majority carriers, which is holes, and the n-type area gets depleted of its majority carriers, which is electrons. So similar thing is happening over here. This area of the p-type whose majority carriers is holes, this area is getting depleted of its majority carriers. So that's what is happening over here. So now what we'll do is we'll increase the gate voltage. So once we increase the gate voltage, let's shift this layer underneath the gate so that we have some room for to show the behavior. Okay, so in this case, what will happen now, when you apply the gate voltage, the most obvious thing that will happen is it will try to repel more and more holes from this area and basically make this area depleted of its majority carriers. That's what will happen. That's the most obvious thing that will happen over here now. So let's see what happens. So if you try to observe this area, see how this particular area gets depleted of its majority carriers, and as and when the holes are getting repelled from this area, it leaves behind negatively charged ions. So let's see how it happens. So you increase the voltage, you see an increase in the depletion area. You again increase the voltage, you see an increase in the depletion region width. You increase the voltage more and more holes are getting repelled, and you see one more layer of the negative charged ions over here. Finally, there is small area on the p-type substrate which converts itself to an n-type material. The voltage at which this particular thing happens, it's referred to as threshold voltage. This phenomena of a semiconductor surface inverting into an n-type material, this phenomena is referred to as strong inversion, and the voltage, this particular voltage at which this phenomena happens, that particular voltage is referred to as threshold voltage. So we started our discussion saying that the threshold voltage is the voltage at which your device turns on. So this is the moment at which your device turns on. You have a channel available now. You have a small, pretty good channel available over here. Now just to apply potentials at the drain and the source terminals, and then this drain will attract electrons from this area, and eventually you see a flow of current. Let's not get into that at this point of time because we have separate slides on them. how the current actually flows, but the point at which it provides a platform, it gets a channel over here, that that particular moment is referred to as threshold voltage. Now, now if you see, the channel over here is completely N type, hence the name is called as N channel MOSFET transistors. So it's called as N channel. So you have an N channel, and MOS is metal oxide semiconductor transistor. So that's where the name comes from. So conversely, if you look into a PMOS thing, let's try to deviate from this one and let's look into what might happen in PMOS. So in PMOS, you have an N-type substrate over here. This will be P plus. This will be P plus, and you have to apply a negative voltage over here, and negative voltage will repel all the electrons from their area, and that all basically conversely it will attract all the holes from the N-type substrate and form a channel and form a channel of all the P-type materials over here, basically P-type positively charged carriers over here. So in the case of PMOS, all these negative charged particles will be replaced by positively charged holes, and you see a P channel forming from the P plus source and P plus drain. So that's where the name comes from, PMOS, basically P channel MOSFET. Okay, so reason for bringing the PMOS topic over here is it will make things a bit clear, so that because we are already in the flow of channel formation, so the names come from basically what kind of channel it is. If it's an N, if this is an N channel, it will be called as N channel MOSFET. If it's a P channel, it will be called as P channel MOSFET. Second thing, the observation is, if you see for an N MOS, it's P substrate. For a P MOS, which will let's say if it sits over here, it will be called as N type substrate. Okay, so let's continue. Let's see now what next. So now if you see, this area is completely depleted of its majority carriers, which is holes. So now there is no more holes present in this area. So now what can happen if we tend to increase the gate voltage, because this is positively charged, and either it has to repel all its like charges, or it has to attract more and more negatively charged particles. So repulsion of all the holes has already been done, and there are no more holes that is present in this depletion region area. So what is the next thing that can happen? It will attract more and more electrons towards under the channel. So further, when we increase the gate voltage, it will try to attract more and more electrons underneath the gate. But the question again comes that where will these electrons come from? So now so to answer that, if you see this heavily doped N plus areas over here, so this will now become the source of your supply. So what this the gate voltage will do is, when this particular plate becomes positively charged, it will try to attract more and more negatively charged particles from this N plus area, and see how it does that. So if you increase the gate voltage, this layer of negatively charged particles will go and sit underneath the gate. It's like this. So if you see, there will be no change in the depletion layer width, because it's already depleted of its majority carriers, and now what you have is only the N plus electrons that will get and sit underneath this particular gate. So this is what exactly happens. If you see this channel area, how this channel area gets increased, and eventually there will be a continuous N channel formation between the source and the drain. So you had the N channel at this point itself, that is the phenomena of strong inversion. You had that N channel. Eventually, if you try to increase the gate voltage, you see a channel which is even more thicker than the previous one. So what can we conclude over here? So we can conclude that the conductivity can be modulated by the gate voltage. Lower the gate voltage, lower the channel width, you have low current. higher the gate voltage, you have higher area, you have higher width of the channel, and you see more conductivity over here. So that's how you can modulate the conductivity using the gate voltage. So that's the first learning that we saw over here. So what we'll do is, since I'm running out of time, in the next video we'll try to see what happens to the gate voltage, or what happens to the n channel formation at the presence of body terminal. So we'll be comparing 2 or 3 scenarios over here. So this scenario we saw with the body terminal is grounded and only the gate voltage. Now what we'll do is we'll apply some potential between the body and the source and see what happens. So let's try to and let's see what is the impact on threshold voltage. So let's try to do all this in the next video. Thank you.